Okay, ich sollte jetzt sogar aufnehmen. Das heißt, ihr dürft euch dieses ganze hochprofessionell veranstaltete Ding dann nochmal auf YouTube angucken, wenn ihr wollt. Alles klar. Yeah, so let's get started. Problem 1, consider the setup for control variance. And then you had this other control variate Monte Carlo method. The advantage for this one is that you you see that this beta is it computes itself. So normally in the version of the lectures you have to choose a beta, and this Monte Carlo method finds an optimal beta by itself, which is kind of nice because you don't need to compute it. Yeah, this is the general setting of this problem. Yeah, and let's get started. Using the strong law of large numbers, show that almost surely this beta n converges to the optimal beta. Yeah, be careful when you apply the LLN, because you have to show that it can be applied, which means the assumption you need IID, random variables, or at least pairwise independent identically distributed random variables, and which is the first point, which is obviously fulfilled. That's no problem. And the second point is you need that this random variable is in L1. This is the second point. And our assumptions in the problem are that that x is in L4 and y is in L4 as well. But for this, for the A, you will see that I'm just going to write it down. Yeah, you see that here you have this product as a random variable, and when you want to use LLN, then the assumptions have to be fulfilled for this product as well, and this is not an assumption, and you have to show that. Yeah, so we have to okay, what are we doing now? We have to show that this is in L1, and this is, it's not given, but it's quite straightforward, because you can either use Cauchy-Schwarz inequality or Hölder inequality. It's your choice there. It's basically the same in this matter, and we know that by, for example, Hölder, we know that this is the second moment, the square root of the second moment times y squared, the square root of the second moment of y. So here we just do some inequality to get this product out of the expectation, and now we have the product of two expectations, and now we can use the assumption that that x and y are in L4. So the second moment exists because the fourth moment exists. So this is finite. So this part here is in L1. is in L1 check. So we can apply law of large numbers. Yeah, this was important. Yeah, and now because of strong law of large numbers, yeah, you can see that well, this just stays the same. This part, well, we just multiply it and have the sums on xi, yi, and xi mu, but we can pull out mu. So we do LLN twice, once on this part and once on the other part. And for the other part, it's just xy. And here we can obviously apply it. And here we have shown that we can apply it. So this converges to, when n goes to infinity, this stays. And the first part goes to the expectation of x, y, minus the expectation of x. This comes from the LLN and the expectation of y. This is just mu. Yeah, and you can see that this is the covariance of x and y. Yeah, and this is what we wanted to show. And yeah, this convergence is almost surely. Yeah, this is what was needed to show. Any questions? Okay. Second one, using 1 and again LLN, show that almost surely this new estimator goes to theta, which is the expectation of x. Okay. Yeah, so where do we start? We start with our Monte Carlo method, which is, so we know in part 2, we start with 1 over n times the sum xi plus beta n mu minus yi. Yeah, this is where we start, and well, we know from exercise from part 1 that this part with the sum and the 1 over n goes to the expectation of x by LLN, and let me write that out. So we have this part, and because this is independent of I, we can pull it out of the sum. So we have beta n times 1 over n the sum of mu minus yi. Yeah, and we have this part here, and well, this goes almost surely to the expectation of x, and this part goes almost surely to 0, because well, this yi with the sum and everything goes by LLN to the expectation of y, which is just mu. So what we have in this part here is just the expectation of y minus the expectation of y when n goes to infinity. So this is 0. And from part 1, we know that this goes to beta star, almost surely. So it converges, so it does nothing weird, doesn't go to infinity, because yeah, when well, x and y both are in L4, so the covariance exists. And yeah, you have just to, well, it isn't on the problem sheet, but just assume that the variance of y is non-zero, and yeah, then you know that this is something finite and exists. Yeah, so, and with Slutsky, which was given on the problem sheet, with Slutsky we know that well, I think we don't really need it, right? Show that almost, yeah, genau. So we know that this goes almost surely to 0 because this is finite, this is 0. So what's left here is this goes if n goes to infinity. Well, just the first part is left, which is by LLN the expectation of x. Yeah, and this was the second one. Yeah, almost surely, because yeah, strong law of large numbers. Any questions regarding this one? Okay. Let me clean the board for another time, because number 3 is kind of long. Yeah, I think I say it very often, but if you want to apply some theorems, check the assumptions, because what basically everyone who tried the part 3, what basically everyone except I think one group which had another approach did was you all applied Slutsky's lemma in the form in which it's on the problem sheet, but because of the square root of n, which is diverging, you can't do it, because only, well, you can see it as a sequence of almost certainly constant random variables, but it doesn't converge to anything. So you can't apply Slutsky here with the square root of n. Yeah. So be careful there. Okay. So what we want to show is show that the limit AD minus theta is equal in law to the limit square root n m beta star n minus theta, which again is equal in law to a Gaussian variable with centered with variance 2 star, where this is the variance of x plus beta star times mu minus y. I'm not going to write it down because I don't have too much space here. Yeah, okay, the second part is quite straightforward because well, you can just consider this random variable beta star, call it z, j is xj plus beta star so consider this random variable. This is obviously IID and has well, exactly the variance we need here. And so long story short, we can apply a central limit theorem. And so this part here, well, we know that the expectation of this z is theta. Because as in the second part, well, take the expectation, this is theta in expectation, this is 0 because you have here the expectation of y minus the expectation of y, so this part vanishes. We only have this one here. So we know that the expectation is theta. So as you can see here, this part is now IID and centered. So central limit theorem, and it has this variance. Going to write that down here. I hope it doesn't get too messy. This is the variance of z, j, beta star for any j, because they're IID. Well, we have shown the second equality. What's left is the first one, and as I said, it is not sufficient to show that this part here is equal in law to this part here because of this square root of n. Well, this may be true. I think it is true that this and this are equal in law, but this doesn't mean that the whole expression is equal in law, because this is diverging. Okay. So what we are going to do now for this equality, equality in L1 implies equality in law. So we will show equality in L1, and for this we consider the sequence. Well, we just subtract one from another and consider this sequence. Well, if you do this minus this, or the other way, this minus this. Well, what have we got then? The square root of n times mn ad minus mn beta star. We just ignore the theta here because it's constant, it's equal, so it disappears. What is this? This is beta n minus beta star times 1 over the square root of n, because somewhere we have this 1 over n times the square root of n is 1 over the square root of n, times the sum n j is equal to 1, mu minus yj. Okay, and if this sequence of random variables converges to 0 in L1, then we know that this equality holds in L1, and when it holds in L1, yeah, the standard convergence diagram, if it's in L1, it's in probability, and if it's in probability, it's in law. Okay, so what we need to show now is the following. We need to show that the expectation of the absolute value of En
yeah, as you might have noticed, my solutions in the exercise class were wrong, so I will do this on the screen here. First of all, in the solutions which should be online by now, there is another reason why we want to show that the expectation of our sequence E goes to 0. It's a nice reasoning with another version of Slutsky, so check it out. It's nice. Yeah, and the point where I messed things up was here. Well, the inequality I wrote on the whiteboard, it wasn't wrong, but the reasoning, how I got there, this was wrong. So the point is we start with the squared first moment, well, the squared absolute first moment of En. The squares just so we get rid of the square roots, yeah, which we get from every inequality we can apply here. So it's just the squares just for notational convenience, because otherwise here we have super many square roots, and we don't like that. Yeah, so this inequality is just normal Cauchy-Schwarz or Hölder. But now the point is we have this here, and yeah, this part is actually just the variance, because if you look at what the variance of this sum is, well, it's the second moment minus the squared first moment, and because in the first moment we have this yj and the minus mu, and mu is the expectation of yj. This part just vanishes when we pull this expectation inside the sum with linearity. And so the squared first moment just vanishes because it's just mu minus mu summed up quite a few times, but yeah, you just sum over 0. So this part vanishes, which only leaves us with the second moment. Yeah, so this identity is true. Yeah, this is the reason why this equality holds. We just write the variance here, and the point now is we can well just pull this fraction outside. You get the 1 over n because you have to square, and because the yj's are independent, So particularly uncorrelated, we can use Bienname to pull the sum out of the variance. Yeah, and then the fraction and the sum, they cancel each other out.
Well, remember what we wanted to show? We wanted to show that this goes to 0. Well, how can this go to 0? This is, yeah, non-zero, but finite. So when this part goes to 0, then we are good. Question is, does this part go to 0? Let's check. So we want to know whether this goes to 0. Yeah, so the solutions say that it's the usual standard calculation. Is this something you know from the lecture, or should I show it? Because I don't think it's obvious, but if you all think it's obvious because you all have seen it 10 times, then I'm not going to show it. Any preferences? Okay, I guess this means I have to show it. Okay, so let's first look at the variance of beta n. This is because we can translate it. This is just the variance of beta n minus beta star, because this is constant. And by definition of the variance, this is the second moment of beta n minus beta star minus the squared first moment beta n minus beta star. Okay, this is what we actually want to consider. Yeah, this is why we're doing this. Okay, let's firstly look at this part. Well, the expectation of beta n is the expectation of, okay, let's do the whole linearity stuff in one take. It's just 1 over the variance of y times 1 over n times n, because we have this, yeah, it's IID, and so the sum just gets n times the expectation of x, y minus mu. Yeah, so where's my pen? This goes to 1, and what are we doing now? Right. So let's write it out. This is squared y. The expectation of xy minus mu, the expectation of x. We can put we can pull mu outside the expectation here because it's constant. Yeah, but the mu is the expectation of y. So what we have here is just the covariance of x and y. So beta n, the expectation of beta n is just the covariance of x and y over the variance of y, which is the definition of beta star. Yep. So we know that this part is 0 because it's beta star minus beta star and squared. So 0 to the power of 2, nothing happens, 0. So we know that this part vanishes. Okay, cool. So we only have to consider the variance here if we want to look what happens with this expression. So let's compute the variance. Yeah, the variance of beta n is, I'm going to write it out, the variance of 1 over n times 1 over the variance of y times the sum of x, y, yi minus mu. Yeah. Okay. What do we do now? Well, these scalars, we just pull them outside. We have to square them because it's the variance. So we have here 1 over n squared times 1 over the squared variance, which is sigma to the power of 4, times the variance of the sum of xi, yi minus mu. Because, well, if we look at different i's, so xi and yi are not independent, but xi and yi are, well, the pair xi and yi is independent of the pair xy plus 1, yi plus 1, something like this. So we can just get the sum outside of the variance because of Biennale, and because this is identically distributed, the sum just gets and times n. So we have n over n squared, and this comes from the sum. So this part is Biennale. Yeah, 1 sigma y4 variance of x y minus mu. Okay, so yeah, we see this is just 1 over n. So if nothing funky happens here, the whole expression goes to 0 when n goes to infinity, because the first part goes to 0 when n goes to infinity. And yeah, why is this finite? Just do yeah, the inequality of your choice here again. Well, we can see the variance of okay, what is it? Yeah, let's just look at this part. This is the expectation of x squared y minus mu squared minus the squared expectation of x y minus mu. Okay, this part goes to this part is finite because of, I think, part 1 of this exercise. We shown that there, and this part is finite. Yeah, because of the same reasoning. We can again apply Hölder or Cauchy-Schwarz, which leaves us with the fourth moment of x times the fourth moment of y minus mu and the square root, but we can ignore that. yeah, and it was an assumption that the fourth moment is finite. Yeah, so for this part, we actually need every assumption. So the fourth moment is finite is well, it doesn't work. It doesn't work with only the second moment, for example, or something like this. Yeah, so this is finite. This is finite. So yeah, this expression is finite. This expression is obviously finite as well. So we have something converging to 0 times something finite. So we know that the variance goes to 0 when n goes to infinity, and we know that this is equal to the variance. Yeah, so we have shown what we wanted to show. Questions regarding this exercise? Okay, apparently not. Okay. Problem 2. Apply the adaptive control variance estimated from exercise 1 to a road network example. Use the same control variant as in lecture 9. Do not forget to compute the variance. Yeah. Here, many of you just estimated the variance of the control variant in MATLAB. So you just you sampled it and then you did the squared standard deviation or something like this. This is unnecessary because well you choose your control variant because you know how it behaves. So there's no need to estimate something there. For your control variant, you should know what your variance is. So you don't do something with the empirical variance, you just compute it. And in this case, it isn't that hard as well. Okay, what was our control variant? I'm not going to write it down. So long story short, this is true. Our control variant y is 1/4 times 32 plus 4 u1 plus 6 u2 plus 2 u3 plus 12 u4 plus 4 u5. Because with the whole x's, it's you can do this by yourself. It's just long, but it's just addition. Yeah, okay, and we know that these u's are all IID uniformly distributed on 0, 1. So we know their expectation is 1/2. So the expectation of y is 32/4 plus, okay, what have we got here? 10, 12, 24, 28 plus 28/4 times 1/2, because this is now the expectation of our use, which is, when you compute it, 11.5. Yeah, this to the expectation. The variance is, well, what is the variance? The variance is 1 over 4 to the power of 2 because we pull this outside. This is a constant, so it doesn't matter. Times the variance of 4u1 plus 6u2 plus 2u3, 12u4 plus 4u5. They are all independent, so we can do Bienname without any covariance terms. So what happens is that we have the variance of 4u1 plus the variance of 6u2 and so on and so on. So we have 1 over 4 to the power of 2 times 4 to the power of 2 plus 6 to the power of 2 plus 2 to the power of 2 plus 12 to the power of 2. Yeah, because well, we got these sums out of the variance, and then we got these scalars out of the variance as well. And when we do this, we have to square them because so this is where these guys come from. Yeah, we know that the variance of a uniformly distributed 0, 1 random variable is 1 over 12. So this is 1 over 12. And if you put everything together, we have 9 over 8 as the variance. Yep. This was the theoretical part of problem 2. Yep. If you implement the adaptive Monte Carlo method from exercise 1, you will see that the table you get is quite similar to the table you have seen in the lecture for beta is equal to 1, which means that because this adaptive Monte Carlo method finds the optimal beta, yeah, and if the results are basically the same, then it's an indicator that the optimal beta is 1. Yeah, this is the learning for this exercise. Yeah. Any questions? Cool. Problem 3 was importance sampling, I think. Yeah, this exercise was really just computations. Let's get started. Okay, we have this W as the fraction of Px and Qx, where both P and Q are densities. In the first case, at 3. In the first case, I think P is the density of a standard Gaussian variable, and Q is the density of a Gaussian not centered Gaussian variable with variance 1. Okay, show that, yeah, W is this expression. This is kind of easy because, well, we know that Wx is, okay, what is P? P is 1 over the square root of 2 pi, the expectation of minus x squared over 2. This is P, and Q is just yeah, the same but different. Minus x minus mu. Yeah, okay. As you can see, the first part just disappeared because it's 1. So what do we have here? We have the exponential of minus x squared over 2 plus, righty? Yeah, I think so. Plus x minus mu squared over 2, which is, yeah, let me write that down, which is the expectation of minus x to the power of 2 plus x to the power of 2 over 2 from the first part here, minus 2x mu over 2 plus mu squared 2. Yeah. As you can see, this part is 0. So we are left with the expectation of mu squared over 2 minus mu x, which is what we wanted to show. Does it help when I switch the light on? Do you see better now? I don't think so. Yeah, this was the first part of problem 3. Okay, the second part was show that the second moment is the expectation of mu squared. This is just analysis. The expectation of W. Oh, okay, we have y here. Okay, yeah. So yeah, we know what W is because we just computed it. So it's the integral over R of W, which is the expectation of minus 2 mu x plus mu squared. Yeah, where did the over 2 go? Well, because it's W squared, it's the expectation squared, And yeah, expectation, I'm sorry. It's the exponential function squared, and well, you can square it or you can just multiply the exponent by 2. Yeah, so there did the over 2 go. Yeah, times the density of y, which is qx. Yeah, and now we already see this part is independent of x, so we just move it outside. We have a 1 over 2 pi from the well, this part comes from q, and then we have the exponential of mu squared. Let's do another color. This is just this. Yeah. Okay, and what's in the integral is the exponential of 2 mu x minus x squared over 2 minus mu squared over 2 plus x mu dx. This part is just this part. And do I have another color? I used to have another color. Let's take red then. Yeah, and this is just this. Yeah. Okay. As you can see, this and this look similar. So yeah, let's just look at this one here. This is minus x to the power of 2 over 2 minus well, it's 2 mu x minus 2 mu x plus mu x, so this is 2 mu x over 2. Yep. Minus mu squared. Yeah, this is just minus x plus mu over 2. So what do we have here now? It's the expectation. Fuck me. Exponential value of mu squared times 1 over 2 pi, square root of that, the integral of minus, nothing to see here, minus x plus mu squared dx. Yeah, this is the density of a Gaussian variable. So yeah, integrated over r, it's 1. So we are left with this part, which is what we wanted to show. Any questions? Okay. Alles klar. Okay. Now we do the same thing. P is still standard Gaussian, but Q is now centered with some positive variance. Okay, we again have to compute we again have to compute W, which is Px over Qx, which is 1 over 2 pi x minus x squared over 2, 1 over 2 pi sigma x where am I here? Oh. Okay. So this is the sigma. Okay, so it's this minus this. So this plus 1/2 x over sigma squared. Yeah, you can see x squared over 2 is in both parts, so we just pull it out. X squared, okay, and this is 1, and this is plus 1 over sigma squared. Is that right? No. Apparently it's minus. Yeah, of course, because this is in the denominator, so this will be plus here. Yeah, now it works. Yeah, so this was the part with W. Questions there? Okay. Okay, and then we again had to compute the second moment of Wy. Okay, let's first assume that case 1, let's assume that sigma squared is bigger than 1 over 2. In this case, the expectation of Wy squared is sigma times the integral over r. Expectation, you know what I mean. Again, here is no over 2 because of this 2. 1 minus 1 over sigma squared q x dx, which is now sigma that right? Yeah, so. So just plug in Q. This is two minus yeah. This is, well, just do the two exponential functions together. Again, we have this, well, this here and this here. So we know that two minus 1 over sigma squared dx. Okay, now we substitute. I'm missing space. Yeah, in the board. You all got this? I think so. I'll just leave it. Okay. Well, now we substitute 1 over gamma is 2 minus 1 over sigma squared. So this part is it sigma squared of gamma. Well, I spare you the details here with the substitution because it's just a linear transformation. So this is something constant, and this is just it's gamma. Pull it on the other side. Pull this into the fraction, and it's just gamma is. Yeah, we might. Yeah, we don't even transform the integral. It's still with x, so we are all good here. It's really just a notational. Yeah, it's for notational convenience. Okay. But this part now is 1. This again is analysis. It's this minus x squared. What is this? I think it's the square root of pi or something like this, and just a bit transformed, and this explains this here. I think I'm missing a minus. So yeah, it's just this reasoning that this is 1. Yeah, so this is 1, and this part is when you put the sigma squared back in. It's sigma over 2 minus sigma squared, and the square root of that. And this is what we wanted to show. Yeah, makes sense now. Is this right? No. I'm sorry. I made a mistake here. This is this, and now it makes sense. Yep, my bad. Anyways, this is what you had to show. And for case 2, where well, case 1 was what did I say? I think sigma squared over 1 over bigger than 1 over 2. Well, if we put it in terms of gamma, this means that this is positive. So case 2 now is if this is not positive. What happens there? Well, it's the same computations, but at some point you will get to this point. Yeah, and because this is okay, we know that this part is always negative, so this part is always positive, so it's always bigger or equal than 1. So we can bound this integral by one dx. This is obviously not finite. Yeah, so we found a lower boundary which is infinite, so the whole expression is infinite. Yeah, this is the reason why we have a plus infinity in the other case we had to show. Yeah, this was problem 3. It was really just analysis. I don't know why this was the exercise, but whatever. Okay, problem 4. Yeah, problem 4 was just MATLAB for stratification. 2 small remarks. Remark number 1, I don't know why you don't like the standard MATLAB functions, but I've seen the most exciting ways to compute a mean. And well, computing a mean in MATLAB or in R or in, I think, every other language is just, well, if you want to compute the mean of a vector, just do mean. It works. So I don't know why you don't want to use these standard functions, but they are correct. They are fast. You can't make any mistakes with them. Just do it. Well, if you did something fancy, then I didn't subtract any points, but it's really just unnecessary. Yep. Another thing on this exercise for the 3 now used proportional stratification with the strata Si, and then you had these strata which were just points, and well, in this case, the strata 0 to 5 are the amounts of what is it here? The amounts of storms, I think. Yeah, rainfall events, right? And these are Poisson distributed, yes. But if you do stratification and well, stratification is some kind of conditioning, and if you have 1 point strata, then you condition on the event that the Poisson variable is I. So if you are in the stratum S2, then you know there were 2 storms, which means you don't have to sample from a Poisson distribution in this case. Many of you try to roll a Poisson dice after getting in a stratum, but in this case it's not necessary, because you know for sure when you are in S2 that it rained 2 times. Well, if you are in, what is it, S6, then you don't know it anymore, because you know it's some Poisson random number bigger than 5, and this is the case where you do have to sample from a Poisson distribution, but in every other case in this exercise you don't have to do that. Yeah. These were my 2 remarks on problem 4. If I found anything in your codes, I wrote you an email. If you didn't get any correction of sheet 5 by now, then I have forgotten you, and I'm deeply sorry for that. Just write me an email. But as far as I'm concerned, I answered every submission, and if I didn't answer it, then I have just, I've just forgotten it, or I missed it, or something like this. This was the solutions of exercise sheet 5. Any questions? Take that as a no. Yeah, gut, ne? Then have a nice weekend. You're free to go. What was I about to say? Exercise 6 is on Monday, 8:30. I hope that I'm able to get into the university again. But 8:30, same room, same time. Yeah, see you.